Hi and welcome to this junior cycle higher level maths video. Today we're looking at geometry and specifically we're looking at transversals and equal segments. Our focus is on parallel lines. So in this video, we're going to understand what a transversal is. We're going to explore how parallel lines cut equal segments on a transversal. We're going to learn about a theorem that talks about equal segments across transversals. We're going to understand what happens when a line is drawn parallel to the side of a triangle. So that's another theorem we have. And we're going to use ratios to describe how sides are divided. We're going to look at how we can use similar triangles in some of these cases and then apply these theorems to solve geometry problems and specifically look at past exam questions. So what is a transversal? So a transversal is a line that crosses two or more lines. So here's an example of it. So here P is a transversal and it intersects three parallel lines, L, M, and N. And it cuts the transversal into two specific line segments, A, B, and B, C. And we care about whether these are equal in measure. So here you can see on the diagram, the length of AB is equal to the length of BC. So we can write that as simply AB in our two straight lines, meaning size or length is equal to the length of BC. You will have already met transversals in the angles video. We work with transversals when we talk about alternate and corresponding angles. In this video, we're going to go deeper and our focus is not on the angles, but on actual lengths of line segments. So the first theorem we're going to meet today is the equal segments theorem. And here is basically what it's showing us. It basically tells us if we have a transversal P that is broken into equal line segments, then across three parallel lines, then any transversal will be broken into equal segments. So here we can see P, which we've already discussed. AB is the same length as BC. So therefore, when we draw in Q, a second transversal, we have the length of D equal to EF. So this is a really helpful tool for us because we know if we can break one transversal into equal pieces, any transversal will be broken into equal pieces. And the theorem is if three parallel lines cut equal distances on one transversal, then they will cut equal distances on any transversal. If this feels very complicated, it's not. Let's get into some examples so you can really make sense of it. So let's look at some really basic questions here. You can see we have three parallel lines in each of these diagrams and there's two transversals. The transversal, so trans is to cross. So the transversal is a line that crosses over these parallel lines. Here we can see that in the first transversal, we are told that 8 is equal to 8 because they've given us 8s on both. So these two are cut in equal segments, meaning these two have to be equal. So x has to simply equal 10. Same over here, we're told 10 and 10. So these two sides have to be equal, so x must be 12. And if we go here, we're told 12 and 12, that's equal segments, so these two must also be equal, so x is equal to 14. Really straightforward. Now, what if we add in a little bit of extra algebra? So here we're told that LM and N will cut any transversal in equal segments. They've told us that that's the bit of writing at the top, which means this equals this. So 12 equals y. So that's perfect. That gives us, let's write it the other way, y equals 12. Then they tell us here that these are also equal, so x equals 10. If we add in a little bit of complication here, then this segment equals this segment. So 3x equals 12, which gets us a nice answer for x as just x equals 4. And then here, this is the trickiest one. So here we have two pieces that are equal. 4x is equal to y minus 6. But we just worked out that x is 4. So that's 4 times 4 is equal to y minus 6. So 16 is y minus 6. We can add a 6 to both sides. And I'll bring it up here. So what that ends up as is 22 equals ry. So then if you want to check that, 22 minus our 6 gives us back to our 16. So the second theorem we're going to look at is about lines parallel to the side of a triangle. So a situation we have here. So in this triangle, the points D and E divide A and B into three equal parts. And by drawing in lines parallel to the base, what we do is we create these points F and G so that the side AC is also divided into three equal parts. So obviously those parts are not all the same size. So AD is not the same size as AF, but AF is equal to FG is equal to GC. Now, this can be broadened to not just be equal in measure, but in the same ratio. So if they were equal, really nice and straightforward. But our focus is going to be looking at when the sides are in a given ratio, or these parts are in a given ratio. So our theorem is if a line is drawn parallel to one side of the triangle, it divides the other two sides in the same ratio. So if this feels confusing, let's work through an example and help you make sense of it. So here we have three parts within this example for us to do a bit of practice. So what we want to understand is the ratio of the sides. So here we have 6:3 on the left-hand side, which we can break down as to 2:1. Should be the same as 5:x. Now you can use your ratio here to kind of scale up. So for example, here 2 by what gives me 5. So I can multiply that by 2.5. Whatever I do to one side, I do to the other. So that's going to give us 5:2.5. Now you might be able to see that much quicker by simply saying, well, 3 is half of 6, so x must be half of 5. And again, that's absolutely perfect if you want to work that way. But I just want you to make sure you have a method that will work in all cases. So then for here, we have 6:4 on the left-hand side, which is 3:2. It should be the same as x:6. Again, we can multiply out to get the bit we want. This right-hand side is 6, so let's multiply both sides by 3. So what that gives us is 9:6. So therefore, x is 9. So that gives us our nice little answer with just using our ratios. But sometimes ratios are not going to be the easiest way to work because we're not going to have a nice method like I know 2 by 3 gives me 6, but that won't always be the case. So let's take a look at this last part. So here I have 3:5 is the same as 4:x. It's quite tricky to get from 3 to 4. So what we're going to do in a case like this is we're going to make a fraction. So a ratio is coming from that word rational, which is another way to say a fraction. So what I'm going to do instead is I'm going to put x over 4. Now the reason I've decided to put the x on top is because I want my unknown on top. So I've decided to put x over 4, and that should give me the same answer as putting 5 over 3. If you wanted to do 4 over x is equal to 3 over 5, that is absolutely valid. You've just made your question a little bit trickier to work with. So in the case where you're not going to get nice numbers in your ratios, I would suggest making a fraction. Multiply both sides by 4 to get rid of my fraction here. And we're left with x equals 20 over 3. And if you want to change that to a decimal, you absolutely can. That gives us 6.6 recurring, so 6.67 if you want to do some nice rounding on it. If you like that fraction method, you can use it all the time. It's just sometimes easier to work with ratios when the numbers are a little bit nicer. So let's look at an example that's a little bit trickier because of the way that they've given us the information. So we are not going to do 8:4 on that left-hand side because the information we have over here on the right, we have that full length. So I want to understand, well, what is this full length here? So that's 12. And then the x is going to be on the top. So what we can do is 8:12 should be the same ratio as x is to 15. So this time we're comparing the top, because that's what's unknown, to the whole, because that's the information we were given. So let's break this down. This gives us 2:3. So if I were to kind of make this something 15, so let me just, so I'm dividing by 4 here. on both sides. And then I'm going to make the right-hand side a 15. So I'm going to multiply by 5. And I'm going to multiply that by 5. And that gives us 10 is to 15. So in order for us to do this properly, this is going to be 10 is to 15. So x is equal to 10. So we're using our ratios to figure out that missing side. Now, in some questions, you may be able to use the idea of similar triangles. So not always, but similar triangles tend to work for the majority of questions we've seen on the old junior cycle, the old junior cert papers and the new junior cycle papers. So when we work with similar triangles, we think of this idea of like a scale factor. How many times bigger is one triangle than the other? Because of the use of parallel lines, we're always going to get similar triangles in this case. So why would we not maybe always use it? Well, sometimes the ratio theorem is easier, and sometimes we won't have the information that we need to do similar triangles. So we're going to have bits of information on the side that isn't a part of the triangle, where it's not a full side of a triangle, it's only a part of it. So it really does have to depend on the information we're given. So I am going to do one using similar triangles, but there is a video that works through similar triangles and working with those, and I've linked that in the description below. So here's an example of a question where we could, if we want to, use similar triangles. In a question like this, the first thing I would say to do is identify that we can use similar triangles. So here we have the same angles because these parallel lines give us corresponding angles. Then we want to break it up into our two triangles. I would always draw these separately, so you can see me pulling out my two triangles here, and then we put our information on it. So here we have a 16. Here we have 14, here we have 10, and here is the side that we want. I like to do a bit of color coding with this. So this side matches this side. We talk about them being corresponding. And then don't get that confused with corresponding angles. So sides that correspond mean they are between the same angles. So you can apply any kind of method for similar triangles. I like the idea of scale factor. So scale factor is how many times bigger. So I'm going to use the yellow side and I do the big divided by the small. So 1.4. So that means this triangle is 1.4 times. Now in this case, well, I should do it the other way. So this smaller one multiplied by 1.4 will give us the bigger one. The bigger one is 1.4 times bigger. So that 1.4 is really important. Z is smaller than the 16. So to make it smaller, we divide by the scale factor. If I wanted to move to the bigger triangle and make it bigger, I would simply multiply by them. So we get 11.4 and then some decimals, but we'll leave it at that. So that's how we could use similar triangles. I'm not going to use similar triangles for any of our other questions in this video. I'm going to stick to the ratio method. But if you want to explore similar triangles in more detail, I've linked the video in the description below. So now let's take a look at question 7b, which comes from the 2015 Junior Cert Higher Level Paper 2. In this example, you can use similar triangles and most students would probably do so, but we're going to use the idea of that ratio theorem we've just talked about. So I've skipped part A, it's got to do with the angles. Our focus is on part B. We can see from the diagram that the side DE is parallel to the side BC. We're told that AE equals 100. AC, so that total length here is 130. We have DE, which is 74. And then we're looking for the value of BC, which I'm just going to call X for convenience. I'm just going to take out our angles here because they're not relevant for the question that we're doing. So what's interesting here is the fact that we're using the ends. So all of the sides are divided in the same ratio. So when we look at the ends, so these are the sides that are parallel to each other, what we need to think about is the fact that BC is the full length of that side and ED is the smaller length. We don't get that difference between them that we get with the other two sides, which means if we're looking at a ratio, we're thinking that 130 is to 100. So that is AC is to AE. So the longer side is to the shorter side. That gives us 13 is to 10. And then that should give us the same as the big side. So just be careful here. X is the bigger side, is to the smaller side, 74. This is a little bit trickier, so we can use that idea of our fractions. X over 74 is the same as 13 over 10. Let's do some multiplication. Let's multiply, I change my color, 74 on both sides to get rid of my fraction, just so the x is really on its own. And then we're going to do 13 over 10 times 74. And that gives us 96.2. What's nice about using this method over the idea of maybe similar triangles is often if we kind of think in terms of similar triangles, we're drawing out two triangles. It's adding in a little bit of extra work. But actually the bones of the question is the same. The maths often looks the same when we're working in questions like this. Now let's look at question 13 part C from the Junior Cycle Higher Level 2024 paper. Here we can use similar triangles as well. If we want to take a quick read through the paragraph, it tells us that a different part of the roof is the shape of an isosceles triangle with base 14 meters. In this part of the roof, Michael makes an attic room by putting two vertical side walls A, B and D, C, shown in the diagram below, but not to scale, and the distance B to C is 8 meters. The total height of the roof is y meters and AB is equal to DC is equal to x, where x and y are both elements of or, which are real numbers. So all that information is given on the diagram. For us to work with the idea of our ratio theorem, what we want to do is break it into one single triangle. So given that this is isosceles, we can split the triangle in half. So here, and we can literally ignore one side. So I'm going to draw this out. So this is what we have. So we know then, because it's isosceles, everything is halved. So B to C was 8, so this piece here is 4. That means this whole section here is half of the 14, so that's 7, and that leaves us 3 here. We have an X and we have Y. So again, because we're using the ends, we have to think in terms of the whole piece. So if I want to get x in terms of y, I'm going to put x on top. So I can say x is to y. So the smaller end of the triangle is to the bigger end of the triangle is the same as 3 is to 7. And it's really important we use the whole length. Y is the whole side of the big triangle, so we have to use 7. This is not going to get us anywhere because we don't have numbers. So what we're going to do is we're going to put x over y and we're going to put 3 over 7. To get that x on its own, we're going to multiply both sides by its denominator, which is y. And that gives us our answer of x equals 3y over 7, which is exactly what they've asked for. Again, we can use similar triangles here, but using this ratio theorem just makes things a little bit quicker, a little bit more efficient. Let's take a look now at question 9 part 2. This is from the Junior Certificate Higher Level 2014 sample paper 2. And again, similar triangles can be used. However, given the fact that we have ED, a portion of the side rather than a full side, ratio theorem is actually going to be easier to work with. First thing we're going to do, we're going to fill in this information that we're given. So A to E is 120, B to E is 80, and C to D is 200, and we're looking for this. Now, you have to be very, very careful when we're working with our end sides because we need to think in terms of the total. So one option here for us is to compare X, this side, to the smaller piece, which is 120, is the same as the difference between EB and DC, which is 120, is to the smaller side. So that is 80. So we can work with this a little bit more. So this simplifies down to 12 is to 8 or 3 is to 2. We want to make that something is to 120. So 2 by what gives me 120? So I can multiply that by 60. Here I can multiply by 60 as well. and that's going to give me 180. So that means the length of E to D is 180. Now you can work with full sides, and we tend to have to do that if we're working with a similar triangle. But here we can see how we can compare those end sides, but we can actually compare the difference between them. Even though we don't see that as its own section because of the way BE and CD are kind of far away from each other, we can still use that same idea. Now let's look at question 4, part BI from the 2019 Junior Cert Higher Level Paper 2. This is a pre-project math, so it's quite an old question. If you've worked through the video this far, I'd suggest maybe pausing the video, trying this one yourself, and then working it through or just correcting your work afterwards. So in this triangle ABC, they tell us that DE is parallel to CB. So that's important for us to be able to use this theorem. And they tell us that A to D is 6, which we can see on the diagram. D to C is 3 and D to E is 7. And they want us to find CB. So let's call that X. So we're dealing with the end of the triangle. Again, that's a little bit trickier. So we're going to say X is to 7 should be the same as the longest side, which for us is actually going to be AC. It's the whole piece. So you have to use the whole triangle. So that's my 9 is to the smaller side, which is 6. Now we can simplify that down, but you might find that actually we're not going to get to 7 very easily. So let's work with our fraction method. I put x over 7, and that's the same as 9 over 6. Let's multiply both sides by 7. If you want to simplify that 9 over 6 first, that's absolutely perfect. You can do that. And then we can work out 9 over 6, multiply that by 7, and we get 21 over 2, or 10.5. So the length from C to B is equal to 10.5. Okay, so here we have a question from actually a Leaving Cert Ordinary Level paper. It's the 2024 Deferred Paper 2 it's question 6B. So you might be like, oh God, this is really, really challenging. But actually, it's a really good example of where we would not want to use similar triangles. It's going to be much more straightforward to work with our ratio method. So the first thing I'm going to do is I'm going to label the side we want, which is this part here. So what we have is 4 is to 7 is the same as x is to 8.4. Now, because these are a little bit trickier to work with, fractions can make the most sense. So if I do 4 divided by 7, it's the same as x divided by 8.4. To get x on its own, I'm going to multiply both sides by 8.4. And that's going to simply give us our answer for x. So it's really nice and straightforward. It's not going to be too taxing for us to work with, and it makes a lot more sense than trying to work with our similar triangle method. So our length from x to v is equal to 4.8 units. So here we have another Leaving Cert Ordinary level question, but again, this is absolutely the kind of level we could expect at Junior Cycle Higher Level. So we have our diagram below. If we read through the paragraph here, it tells us that DE is parallel to FG. That's really important because without that parallel, we can't kind of use this ratio method. And then it tells us DH is 5, which you can see on the diagram. HE is 12, which we can see on the diagram. HG is 30, and DF is X, and we want to find a value for X. So the first thing we want to realize is if we're working with this side here, they've broken it into 2 parts. So I need to understand this length here, which is actually not bad. It's quite straightforward to do because we know the whole length is 30 and that little length is 12. So that's going to leave us 18 centimeters here. That 30 really is not going to get involved for us. So we know from this side here, we can do 12 is to 18. I can break that down. So think about what you can divide into it. The biggest number is 6. So that gives us 2 is to 3 is the same as 5 is to x. Now it's up to you. You can use the idea of fractions here, but you can probably think, well, how do I get from 2 to 5? Multiply by 2.5. And then you can do that on both sides. So this gives us 5 is 2, and then we get 3 by 2.5, and that gives us 7.5, which tells us that x equals 7.5. So again, another example of where similar triangles would definitely make our lives harder than they needed to be, and understanding how to use this ratio theorem is really, really helpful.